So for a transverse wave, we can find a relationship between the distance concepts and the time-related concepts like period and frequency. So if you look at this wave, as one goes through the window and then another comes along, it traveled one wavelength from crest to crest, and the time it took was one period. So if we know how far it traveled, wavelength, and how much time it took, we can find the velocity of a transverse wave. So let's look at wave speed. Waves travel one wavelength of distance in one period of time. By definition, the period is the time it takes a wave to travel one wavelength. For one complete wave to pass a point is another way of looking at it. Another way of looking at it is for simple harmonic motion, back and forth motion of one point. Okay, and during that time, it has traveled one wavelength. So the velocity is how far it traveled, lambda, divided by the period. So we really, if we write that as lambda equals 1 over the period, which is the frequency, lambda times frequency, but we generally write it as v equals f lambda. So this equation allows us to relate frequency, wavelength, and velocity. We use this wave speed in two different ways. One is that v equals f lambda. So, I'm not going to go through all the iterations of this, but bottom line is we can relate the frequency, the wavelength, if we know the velocity, or, if we know any two of these three, we know the third. The other is v equals delta x over t. That still exists. So, but that's a little more with how the wave travels from point to point. So if you're talking about wave characteristics, you're generally talking about this v equals f lambda. On the other hand, if you're talking about it goes from point A to point B, we can use just the standard velocity equations we had before. This is Coach, who had a starter pistol, and I think we were about 180 meters away, 160 meters away. I shouldn't say it, that's me, but we had a camera here in the school observing what goes on. Now I'm going to play it twice. So what happened was you saw the smoke, the shot went off. The light gets there almost instantaneously, and we'll talk about the speed of light in a second. But that sound took a while to travel that 180 meters. And so if we do that again, notice that difference. And if you know that distance and you know the time that it took the sound to get there, assuming that the light got to the camera almost instantaneously, then we can calculate the speed of sound. And that speed of sound ends up being very close to 331 meters per second. And so 331 meters per second at standard temperature and pressure. So really at about 0 degrees Celsius. At room temperature, it's closer to 342, 343 meters per second. So the nice thing is we can use these numbers. In fact, anytime, if you ever want to use 331, that'll work just fine, unless they tell you another number. But on tests for me, I allow 331, 342, anywhere in that range. So these are mostly known speeds. Sound we just talked about, but light is a known speed. It has a special symbol, c, and it's 3 times 10 to the 8th, that's the way I write 3 times 10 to the 8th for presentations, meters per second in air or a vacuum, slightly slower in other materials. But if you have situations where you're talking about how fast did light travel in air or a vacuum, we can use this. So it's a known thing. That's nice because both of those velocity equations, we can plug in numbers that we know. Here's an example, or 4 examples. The sun is so many meters from the earth. How long does it take the light from the sun to reach the earth? So if you knew how many meters it is from the earth, and you know the velocity, you just do v equals delta x over t, and you can find that time. So that's a traveling from point to point. Red light has a frequency of so many meters. What's the wavelength? Well, if we know the speed of light and we know the frequency, we can calculate the wavelength, v equals f lambda. A flute makes a note of 440 hertz. What is the wavelength? Well, if we know the speed of sound, and we can assume 331, unless we're told otherwise, and we know the frequency, we can find the wavelength of the sound. I yell. The sound echoes off the back wall 5 meters away, so it's traveling. It goes from point to point, really goes off the back wall, and comes back. When do I hear the echo? And we know the speed of sound. We know the distance, and that's a little interesting because echoes, or reflections if we're talking about light, what happens is the sound travels to some object and then travels back. So the total distance is twice as far as the distance to the object. If you have echoes or reflections, it's sometimes useful to draw a picture. So if we know the velocity here, if we know the velocity is, let's say, 331, and we know v equals the distance divided by the time, then if we know how far it is to that wall, the distance it'll travel is twice that, and we can solve for the time. Alternatively, if we know how long it took the echo to get back, and we know the velocity times time will be how far that wave traveled during that time, and we could figure out half of that would be the distance to the wall. So these speeds of waves, the problems that we solve with that are really not that complex. Just v equals delta x over t that we did before, and v equals f lambda, that's new. But we have the advantage of being able to assume numbers for the speed of light and for the speed of sound.